Hi, my name is Hildebrandt, and today I'm going to be talking about physical test coverage for autonomous vehicles. Let's begin. So autonomous systems are here, and it's not just one or two companies that are working on this, but there's several, and each may have thousands or hundreds of thousands of vehicles operating on our roads today. With that being said, these systems are failing, and they're not just basic failures like disconnects. These are serious failures resulting in the loss of human life. But they're being tested. Waymo's driving millions of miles, Tesla's driving millions of miles, and there's even standards that are being developed to help test these systems. So then the question is, well, where's the disconnect? We have these serious failures resulting in the loss of human life, but we are testing. We think that this disconnect is because we can't answer some basic questions about the system, like, was the previous test useful? How thoroughly is the current system tested? Or when is it safe to stop testing? More specifically, how do we quantify an autonomous vehicle's test adequacy? So to understand why we can't do this, let's first understand how we do it for traditional software. So traditional software has the following flow. You have input, which goes through a system, and then goes to some output. That system is generally software. And if we want to know how much of the input space we've seen, we can look at abstractions of the software and look at things like statement coverage, branch coverage, or function coverage. And if we know that 92% of all statements are covered, then we know that there's probably a large portion of the input space that we've seen. Okay, so why can't we do this with autonomous systems? So let's start with the basic system and see how it differs. The first difference is that there's an environment. That is, your output changes where you are in this environment, which changes your sensor data. And this sensor data is complex, and there's a wide variety of it. You have cameras, LiDARs, GPS, sonar, radar. And on the other hand, the environment is practically infinite. The number of possible scenarios is just unimaginable, meaning that creating any sort of abstraction is very difficult for it. The other difference is that the system is no longer just software. It's software and hardware. And this hardware has a state. And the state is dependent on the type of hardware being used. So whether you're implementing a truck or an airplane or a drone or a car. So this environment and state are two key factors which drive the behavior of autonomous systems, and they're not currently being included in metrics used today. So for example, if we were to look at some of the other metrics that are being used, you can see that both the environment and the state are not accounted for or only partially accounted for. We want to introduce physical coverage, which directly includes the environment and the state into the metric. Well, how did we do that? We know that the environment is highly complex and practically infinite, and we know that the vehicle state is highly dependent on the specific hardware. To solve the first problem, we said, okay, well, this environment is practically infinite, but only a portion of the environment is important. First, only what we can sense is important. If your vehicle can't sense something, it can't affect its behavior. Next, we only need to work to consider a portion of the environment which your vehicle can reach. This is similar to saying if I'm driving down a highway, I'm considering only what's directly in front of me and 100 or maybe 200 meters away. Whereas on the other hand, if I'm in a parking lot, I'm worried about what's around me in all directions, but only for a much shorter distance, maybe 2 to 5 meters. Okay, so that covers that. How do we then include the state into the system? Well, we can use kinematic models as a way to abstract the state for any vehicle or any hardware configuration. Now that we have this insight, let's see how we use this to implement our system. Here's our system, which we call the pipeline the RRS pipeline, which I'm going to explain using an example. It starts with a test. The test could be, for example, driving down a road from point A to point B. Next, we know that this environment or test has a big environment that's practically infinite. So we first look at what the autonomous vehicle can sense, which is represented by the green dots in the box on the bottom left. Next, we compute the reachable set. That is, given the current state and the kinematic model of the robot or autonomous vehicle, what is the area or volume that the vehicle can reach in a given time frame? Then we compute the intersection of these two, which we call the sensed reachable set. Finally, we vectorize this using the centroid to boundary method, which states you take a point and you measure the distance between that point and the boundary of a shape at set intervals. And if we know the magnitudes of each of these measurements, we then have a vector, which we call a RS vector, which represents the sense reachable set. And you can see this working for an example below. So this is from Waymo, which is a real-world self-driving car made by Google. And you can see that the vehicle's driving on the top left. You can see on the bottom left the vehicle's sensed environment. Then we have the sensed reachable set represented by green in the bottom middle box. On the bottom right, we have the vectorization. And finally, we have the RS vector shown in the middle on the right. So then you might ask, okay, well, how do we compute physical coverage? Well, physical coverage is the number of environment state pairs that we've seen over all possible environment state pairs. In our case, the numerator alpha is all RS, the set of all RS vectors that we've seen given the entire test set. And beta, which is the denominator, it can be computed because we know that the approximation RS has a starting point of all zeros and an ending point of x, where x is the maximum size of the reachable set. And then as this test suite starts to increase and the number of tests we have start to increase, our physical coverage will increase and eventually saturate if you're operating in the same environment. We couldn't cover all the details here, and we highly encourage you to read the paper to find out more. With that being said, let's dive into the study. So we asked 3 different research questions, which I'll explain as we answer them. To do this study, we used 3 different environments: Highway N, BeamNG, and Waymo Open Dataset. I'm going to focus on the latter 2, which are the 2 most realistic. BeamNG is a high-fidelity simulator where we ran 10,000 tests, and the Waymo Open Dataset is a dataset provided by Waymo with real-world driving data, where there was roughly about 4.5 hours of driving data that we used. Our first research question said, how effective is RS at grouping equivalent environment inputs such that they cause similar behaviors? So for example, here we can see a vehicle that's crashed as well as a vehicle that's driving down a highway. If we were to look at PhysCov, we would hope that they say they're different. To better understand how we answered this, we need to understand what an equivalence class is. An equivalence class says that given 2 tests, if they're grouped together, they're an equivalence class. An equivalence class is consistent if both of these tests showcase similar behaviors. So for example, here on the bottom left, we can see 2 vehicles driving down a similar highway under similar conditions. So this is a consistent class. At the same time, here's 2 vehicles driving down similar highways under similar conditions where they both crash. This is still a consistent class because they show the same behavior. Finally, we have 2 vehicles, one that's driving down a highway and one that's crashing. This is an inconsistent class because your metric has grouped these 2 into the same equivalence class, yet they're different. We then went and measured the number of classes, as well as the percentage of consistent classes over several baseline metrics, as well as several versions of PhysCov, specifically Psi1 to Psi10, which just represents the length of the RS vector. Here are our results. We can see that line, branch, and interprocedural prime path coverage generate very few equivalence classes. This represents that they have a very coarse approximation, showing that they're not able to adequately identify between different behaviors in the system. On the other hand, you have interprocedural path coverage, absolute path coverage, and trajectory coverage. This generates a class for every single test. This indicates that it's generating a way too fine abstraction where it's unable to identify any similarities between any of the given tests. Physical coverage, on the other hand, is somewhere in between, where it's able to vary the number of classes between very few and many, depending on our approximation strength. Additionally, if you look at consistency, we find that the best consistency for classes is 58% for our baseline metrics. Our worst is 7%, which is better than their best. Furthermore, as we increase our approximation strength, we reduce the percentage of inconsistency. Next, we try to look at we answered the question, how effective is PhysCov at selecting tests that induce unique failures? More specifically, if we were given a set of tests, we would want to select the set of most unique tests. For example, we can see that these 2 tests are very similar, and when we produce a final test set, we'd only want to select one of them. And by doing this, we'd hope that we find more unique failures. So here's our results. On the y-axis, we have the number of unique failures. On the x-axis is the test suite size. The blue line represents if we were to randomly select a test set. So for example, if I was to select 50 tests randomly, I'd expect to find 11 failures. On the other hand, the orange line represents if we were to select tests that try to maximize the physical coverage that we see. When we do this, if we were to select 50 tests, we find that on average we found 55 unique failures. We are able to find more failures than tests because a test may contain more than one failure. If we minimize physical coverage, we find that we're also able to minimize the number of unique failures. This answers the question that PhysCov is good at selecting tests that induce unique failures. Our final research question looked at the real world and asked, can PhysCov distinguish between similar and different real world scenarios? So for example, here we can see a Waymo driving down a very tight single lane road and Waymo driving down a highway. If we were to use PhysCov, we'd want them to say they're different. So to do this, we looked at 3 different scenarios. So for example, a parking lot, driving down a 1-lane road and driving down an empty 2-lane road. We computed the RS vectors for each of them, and when we compare them, we find that there's very little overlap between the two. This indicates that PhysCov is able to distinguish that these are different scenarios. At the same time, if we pick 3 very similar scenarios and again compute the RS vectors and compare them, we find that there's much more overlap, indicating that PhysCov is also able to distinguish that these are similar scenarios. But this works both ways. Imagine you wanted to ask for a very distinct or similar test set. So let's start with the similar test set. You can say, hey, let's look at the RS vectors with the most overlap and then find the tests that they relate to. These are the tests that relate to this example, and we find that 2 look very similar. That is because these 2 tests actually stem from the same root test, and Google spliced them and gave them as 2 separate tests in the dataset. On the other hand, imagine you wanted to find tests that are extremely unique. You could again look at the RS vectors, find the RS vectors with the least overlap, and then find what these RS vectors, which tests they were from. And when you do that, you find an intersection, a 4-lane road, and a 1-way road where there's vehicles on either side, which represent 3 very different scenarios. So that concludes our talk on PhysCov, where we've presented a new and novel physical coverage metric for autonomous vehicles. Thank you.